In this presentation, we are going to look at the paper Lessons from Giant Scale Services. This paper looks at a basic model for sites in giant scale services, the challenges they face with availability, being on the internet and all, as well as the way these sites can evolve and grow. Some of the arguments he makes comes from other articles or books, so the conclusions he makes are not absolute, rather conclusions he comes up with based on the principle he's studied. The reason he does this is because he wanted to look at the services at a high level. At the time this article was written, this was a relatively new concept, so that was a factor as well. This paper looks at infrastructure services that use the internet to provide services such as sending messages. They want the basics of giant scale services to have the scalability and availability that is needed in the real world. Some of the advantages of these services are that they have the ability to access the server anywhere at any time. You can also connect from different devices such as a smartphone and computer. The paper talks about groupware being an advantage. Groupware is any application that can be accessed by another person, such as a shared calendar or phone conference over the internet. Another advantage is the cost being lower. The resources used can be used by multiple users instead of end-user devices that will only be available to one user even if they aren't actively using the services. Lastly, the paper talks about the updates being an advantage. Updates in this system are more simple and easier to accomplish than other updates at that time. There isn't any need for a person to have to come to your house to update your devices. The updates are done remotely. Next, we're going to talk about the components in the basic model. First, there are the clients. These are just separate web browsers. Then there is the IP network that is needed to let people access the service. The load manager keeps the availability safe in the event of a server fault. It also balances the load across the active servers. The servers themselves work to combine the CPU memory and disks so that they can be duplicated easily. Next, you have the data that will be stored by a replicated or partitioned database. This data is stored across the server's disks. It isn't necessary, but a lot of servicers use a backplane. It handles traffic within the servers. Here is one of the diagrams from the paper that shows the basic model. The clients connect through the internet and then they go through the load manager that will balance the traffic of the site. Next, we're going to take a closer look at the load management. The original way to go about the load management is to use a round-robin technique. This will pass out IP addresses to clients one at a time, taking turns to evenly pass them out to the clients. This will balance out the loads, but it doesn't hide the inactive servers. Any client that has a node's address that is down will keep trying to use it. It does this until the DNS mapping expires. Most of the load management systems are layer 7 switches. They know HTTP requests and will parse URLs. They will find when a node is down. It does this by watching the TCP connections when they are open, so it knows when a node goes down. This causes it to isolate the down nodes. Custom front-end nodes work like the service-specific layer 7 routers. They differ from switches by having the nodes follow the sessions information of each of the users. The last approach this paper talks about is the smart client end-to-end approach. This approach includes the client in the load management processes whenever it can. This diagram on the top shows a simple load balancing technique. A round-robin DNS that will assign a server to a client and so on. The data is duplicated so that all of the nodes are the same, which means that they are able to process any query at the time. The diagram on the bottom is showing a search engine cluster. It supports programs such as web servers. The programs connect through layer 4 switches, which will make sure it doesn't show any faults and has a balanced load. The data is spread across the servers. By doing this, it will increase the aggregate capacity. A downside of this is that the data will not be able to be accessed if the server is down. As you can see on the bottom figure, the nodes access the data through a backplane. Now we're going to look at giant scale systems high availability. First, we're going to look at the way to measure availability. The traditional way to measure it is by looking at uptime. As explained in the paper, uptime is the amount of time that a site is handling traffic. When dealing in uptime, we measure it in nines. So, for example, 3 nines would be 0.999 uptime. So, this first equation, we see the difference of MTBF, which is the mean time between failure, and MTTR, which is the mean time to repair. This difference is divided by the mean time between failure. This equation shows us that in order to improve the uptime, we either need to reduce the frequency of failures or we need to reduce the time it takes to fix failures. Next, we're going to look at the yield. The yield is the number of queries that are completed over the number of queries that are offered. The yield and uptime are normally pretty close, but the yield can be more useful because it doesn't look at all the seconds equally. If the server is down for a second but has no queries, it will not have any effect on the users. Whereas if you look at this in terms of uptime, the uptime will be reduced even though it's not benefiting the users. Lastly, we're going to look at the harvest of a query. This is the data that is available divided by the complete data. Ideally, you would have 100% harvest in yield, which would mean that every query would be completed successfully and the entire database would be reflected. On this slide, we are going to look at the DQ principle. The DQ principle is the amount of data that needs to be moved per second on average. This is shown by the data per query times the query per second. The basis behind this is that the capacity of the system normally tends to bottleneck. This will reduce the amount of data that will be able to move. So we need the DQ value to show how much data should be moved at a time. To be able to adjust the DQ value, first the ideal workload needs to be decided. Then a load generator needs to find out what combination of hardware, software, and size of database needs to be used to have the ideal workload that was decided on. If nodes were bought at different times, they could have different values, so the load would need to be partitioned unevenly. The DQ value will help distribute the load evenly by telling us how much should go to each node. The DQ value also comes in handy when talking about future hardware and services. If the DQ requirements that are needed are known, the kind of hardware and software that will be needed will also be known. By knowing the DQ requirements, targets are set up for the future hardware and services. The goal for high availability is to control how DQ reductions will affect the previously mentioned available metrics. Next, we're going to look at the differences between replication and partitioning. Replication is the technique that was originally used. It has previously been thought of as better due to the fact that it keeps 100% harvest during a fault. But with dual analysis, we see that the replicated version goes down to 50% harvest. With partitioning, the harvest drops to 50% when under fault, but with dual analysis, it stays at 100% harvest. With both replication and partitioning, the DQ value starts off the same, and they both drop to 50% with a single fault. Normally, replication will just assume that there is enough space to make it where if there are any faults, it won't affect the yield. This is called the load redirection problem. This means that whenever a node fails, the queries have to be handled by the remaining replicas. For replication, it is cheap on the disk, but it uses DQ points to access that information. When it is truly replicated, you need 2 copies of the data, but that will use twice as many DQ points. Even though more copies are needed in replication, using more storage space, the main cost that you need to worry about is the DQ bottlenecking that takes place. So the DQ constant doesn't change based on if the database is replicated or partitioned. So there is no real savings by using partitioning over replication when it comes to the DQ value. When it comes to partitioning the database, it makes more sense to partition it thinly so that there are not as many replicas. This can be done without having any difference in the DQ value. So once the database is partitioned in convenient sizes, it can then be replicated. This makes it easier to control the harvest, disaster recover, and to grow the system. It allows the system to grow by replication rather than repartitioning the data onto more nodes. Lastly, the data can be replicated based on the importance of the data. This is so that if a fault occurs on one of the main nodes, another node can deal with the more important data. It will still lose some of the data, but it will be the data that isn't as important. On this slide, we are going to look at graceful degradation. Even with a good design, saturation cannot be avoided at a reasonable cost. This is because the peak average ratio can go from 1.6 to 1 all the way to 6 to 1. So it can cost a lot to build out the capacity it can maintain since it is far above the normal peak. Also, there are single event bursts, which are times that the site could experience more traffic than normal. There's also some faults that are not independent, such as power failures or natural disasters. The nodes that didn't fail will become saturated and the overall DQ value will drop. The big thing to take away here is that graceful degradation is managing how the availability is affected by saturation and how we can decide how that saturation will affect the uptime, the harvest, and the quality of the services being provided. On this slide, we're going to look at disaster tolerance. Disaster tolerance manages the replicas with graceful degradation. A disaster, as defined in this paper, is a complete loss of one or more replicas. Whenever there is a natural disaster, it could affect an entire physical location's replicas. When there is a more centralized disaster, such as a fire or a power outage, only one replica could be affected. We need to find out how many locations are needed and how many replicas does each location need to have. To solve the load redirection problem there, we are going to take a look at the following table right below. So with the example that the paper gives us, if 2 replicas are at each of the 3 locations, they would be expecting to lose 2/6 of the replicas if a natural disaster were to occur. This means that the sites that didn't go down during the natural disaster would have to deal with 50% more traffic than normal. This 50% would saturate the site, causing the need for graceful degradation techniques. When it comes to load management, though, disaster recovery has a harder problem. Layer 4 switches don't help with the loss of an entire cluster. The external site name might not be available at all during a disaster. Whenever this happens, the traffic is redirected to other replicas through DNS changes or smart clients. Next, we're going to talk about online evolution and growth. So when it comes to these online services, there are many continuous updates that have to be done, whether they are for growth or just for functionality. With how many updates that are produced, it means that there is always something to fix. Because of these constant updates, the acceptable quality is all about if the software meets the target mean time between failure, low mean time to repair, and does it have any cascading failures. All updates and scheduled maintenance are scheduled failures, which is basically just the online evolution process. It's important to complete these updates without taking the site down. With the number of updates and maintenance required, if the site was down every time there was an update, the site would never stay up for long. When we think of the online evolution as temporary, it reduces the DQ value. Due to this, we can reduce the influence of the DQ value on our available metrics. Next, we're going to look at this formula for the total DQ loss. The online evolution needs a fixed amount of time per node, which is the U in the following formula, and N is the nodes. So we have the change of DQ is equal to the nodes times the amount of time per node times the average DQ value per node, and that equals the DQ value times the amount of time per node. So this breaks down to the loss DQ value is the total DQ value times the upgrade time per node. On this slide, we're going to talk about the different approaches to upgrading the site. The time it takes to upgrade software can be done quickly when handled using a staging area. The staging area lets the new and old versions both be on the node. The three approaches that we're going to look at are shown on the figure below. I kind of think it's easier to see what they're talking about when you look at that. The shaded regions show us the DQ loss over time for a 4-node cluster. So the first approach is the fast reboot. This is the simplest because all that happens is that all the nodes do a quick reboot into the new version. This will require some scheduled downtime though, but by doing this during off hours, the loss of yield will be lesser impacted. Next is the rolling upgrade approach. This approach will upgrade the nodes one at a time in waves. This will reduce the impact because there will only be one node down at a time. A disadvantage to this approach is that the old and new versions have to be compatible with each other because one node could have the new node upgrade and still have to communicate with the nodes that haven't gotten the upgrade yet. Lastly is the big flip approach. This approach is to update half of the clusters at a time. This will cause half the nodes to be taken down, upgraded, then the other half be taken down and upgraded. Whenever this occurs, all the traffic will go to the other half of the cluster that isn't down. This approach is very powerful and can be used for all kinds of upgrades. All of these approaches have the same DQ loss, so in the graph they plotted their effective DQ level against time. The three approaches have the DQ loss spread differently over time. All the approaches are used, but the rolling upgrades are the most popular. And the big flip approach is really only used for more complex changes and not used quite as often as the others. So, in conclusion, this paper has shown different lessons that the author learned for developing giant scale services. The first lesson is to get the basics right. Next, everyone needs to decide on the goals and how to measure them. Next would be that everyone needs to remember to focus on MTTR at least as much as MTBF. Next, you need to understand load redirection when there are faults. Graceful degradation is an important aspect of a highly available system. The next lesson would be that DQ analysis should be used on all of the upgrades. And lastly, automated upgrades should be used as much as possible, like rolling upgrades and that kind of thing. These techniques address some of the key issues that exist and provide a different way to think about availability and fault tolerance. And that is it.